Weipeng Zhou. I'm a postdoc associate at the Professor Huaqi's lab. And previously, I was a Ph.D. at the University of Washington, advised by Meliha Yetisgen. Today, I'm going to talk about foundation models for electronic medical records, and I will be reviewing two recent papers. So the first paper will be Foresight, which was published in Lancet Digital Health April this year, and the other one is EFO from MBJ Digital Medicine, September this year. So the first paper will be Foresight, a generated pre-trained transformer for modeling of patient timelines using electronic health records, a retrospective modeling study. Electronic health records is a digital version of the patient's paper chart and provide comprehensive information for the patient. It could be held to improve the patient care, and it could be used for coordinating efficient care. There are structured data in electronic health records and also unstructured data. The structured data contains the information such as demographics and diagnosis codes, and unstructured data could be the clinical narratives and something in the imaging data. So we can do forecasting with EHR, which will be predicting the future events using the previous historical data. So the current studies have the limitation of using just the structured data, and they are limited to a specific time frame. But text data is about 80% of the patient data, and it provides granular view of patients' biomedical history. There are several existing EHR large language models that's trained on structured data, such as this BHR-BERT, which stands for BERT for EHRs. It only uses a small subset of disorders from the structured electronic health records, like 300 of them, and it forecasts disorders for the next visit on a predefined time frame, which is just 6 or 12 months. There's also the GBERT, representing the graph neural networks and BERT. And for this model, the inputs are all single visit samples, which not capture long-term contextual information. It's also only used structured data. MedBERT is another EHR LLM. It's trained on structural diagnosis data using ICD codes, and it's fine-tuned for some more downstream tasks using, when it was pre-training, it used the mass language modeling task. It's also limited just to ICD-10 codes. So the objective of this study is to train models using unstructured text and also structured text, structured information such as age, ethnicity, and sex. It's using the GPT-3 approach, which is to do unsupervised learning by predicting the next token. It's also able to do multiple tasks without fine-tuning, the zero-shot capability. So for example, forecasting the risk of disorders, diagnosis, etc. It's also validated across data set from different hospitals, and they also develop a web application for showing the model. So the pipeline of this tool or this large language model contains the COG stack, which is the data retrieval and data preprocessing tool. It's followed by a medical concept annotation toolkit, the MedCat, which structures free text information from EHRs. And there's the Foresight core, which is just a deep learning model, and the GPT model. And there's the web application for interacting with the data sets. So here is a pipeline, visualized pipeline. The data comes from the hospital, and then it's processed using a COG stack. The documents were also processed using the MedCat, which extracted entities from the text and normalized them into structured data. It's then combined with structured data like diagnosis codes and demographics information. The combined data set will be used to train a GPT-like model using the next sequence prediction task. So the data set they use contain the King's College Hospital, around 1.5 million patients, and the South London and NHS Foundation Trust, around 27,000 patients. And then the Mimic3 data set containing 46,000 patients. Here is a distribution of the data sets. We see the KCH and SLAM contain around 50% white, but for mimicry is around 70%. And KCH for female, the KCH, SLAM, and mimicry is around 50, all around 50. And for the patients who are older than 64, we saw KCH is around 22%, and SLAM is 10%, and mimicry is around 50%, which is a very big difference. To extract the concepts from clinical notes, they utilize the MACAT and then first extract the free text, and then they perform linking to SNOMED ontology. They extracted the disease symptoms, medication findings, and other concepts. They also remove concept occurring fewer than 100 times to drop the long tail, making the model more robust for the frequent ones. And they also group the concepts by patients and organize them into timelines. They suggest that the concept frequency threshold ensure enough data for meaningful analysis, but also protected patient identity by removing the rare concepts. They then split the data set into 95 to 5. The foresight, which is the core component of the pipeline, is a transformer-based model built on GPT-2, perform next token predictions, and in comparison to BERT, it's single direction, so it does not look at the future. And this is a potential advantage because GPT was able to do some vision interpretation. So they think that using this structure, following this structure, they'll be able to implement similar things in the future. In contrast to the next word prediction in standard text modeling, they perform the next concept prediction. So for the task, we have a list of patients, U1, U2, U3, and for each patient, we have a sequence of events, W1, W2, W3. A training objective is when given the previous sequence of the patient, predict the current concept and minimize the loss. They perform hyperparameter selection, which was done on the 5% of training set at the KCH hospital. And they selected the 16 layers, a GPT with GPT-2 with 16 layers, 16 tension heads, embedding dimension of 500, weight decay, etc. They only took 1 to 2 days for training all the models on the A100 GPU. And this web application, they have web application available online.
That much on B100?
Yeah.
So if one document have 50 concepts all extracted, right? How do you, they just order the concept by the sequence of occurrence in the document?
Yeah, I can show you. I can show you the web application they developed. So this one, this is the web application. So, and then this is the way they organize the concept. So ethnicity, white, sex, female, age 45, etc. And then the SEP, then to the next one, next block, disorder, age, etc. And if you click the predict, it will predict the next concept with the probability. So here we see this rhinitis is displayed, and also common code. And here you could switch from between different models. So we have KCH, SLAM, mimicry. They train different models on different data sets. And you can select whether you want to see the new concept or want to see the recurring concepts. Recurring concept means that something that have already appeared before. And here you could select whether you want to see the disorders. Here I selected disorder, but you could also see medications Probably takes some time to load, but yeah. And it also offers some type of interpretability. By clicking the saliency, you can see that some of them is darker than another, which means that these concepts have some contributions, have a high contributions to this prediction. So that was just a qualitative view of the model, but next we'll present some evaluation metrics. They have their own metrics by extending precision and recall. So they also have some heuristics for this kind of task. When doing the concept forecasting, they forecast the next concept at each time point of the patient's timeline, and they hypothesize that the factors could be influencing the prediction could be the order of the concepts, data in EHR, some delay diagnosis, the chronic disorders without a precise start time. And based on this hypothesis, they define 3 thresholds for evaluation. So 30 days means a immediate short-term future, whether the concept will appear in the next 30 days, and 1 year, as well as infinity, which is all remaining, whether a concept will appear in all remaining patient data. And the forecast considered correct if the predict concept appears within the time range, if it's not exact next entry. They also calculate the metrics based on top N because they want to see the top 1, top 5, and top 10 accuracy, precision, and recall. They also, so in the previous web application, we see that they're able to show whether it's a new or recurring concept, and they try this before as well. For the NLP extractor, they created 17,000 annotations at KCH and splitting that into training and test set. They found the training model found it achieved 0.9 accurate, 0.9 precision, 0.8 recall, and 0.8 F1 score. And besides concept extraction, they also explore the extracted characteristics of the concept, whether it's experiencer or negation. Experiencer means that whether the concept affects the patient or somebody else. Negation means that if the concept is affirmed or negated, and they're both above 0.9. They also reported the training and validation loss of the foundation model around 3 for all of them. And this is the performance metrics for the KCH and SLAN and MIMIC3 for disorder specifically. So we see at KCH at 1 and 30 days, it has a precision of 0.55, recall 0.47, which is this row by taking the average. And we see that for the new concept, it's very low, just 0.3 precision and 0.2 recall. But for the recurring one, it's got 0.8 precision and 0.72 recall. It then tried to increase the time range of prediction, which means it will be correct if the concept matches any of the the rest of the patient sequence, so infinity. We see that the score also increased from the average score increased from 0.5 to precision increased from 0.5 to 0.64, average recall increased from 0.47 to 0.54. And they also try seeing the top 10 accuracy, KCH at top 10 accuracy. We see that it's much more higher precision and recall, increasing from this 0.3, 0.2 to 0.68 to 0.53. They also reported their model architectures search result. So increasing the product heads and layers up to 32 times 32 did not improve performance. And after that, it's overfitting. Model trained on bucket size of 1 day outperform models trained on larger bucket size. which is defined to be the size of the smallest time span the model can differentiate. They also try LSTM models as well, but they found it to perform 40% worse than a GPT model. One interesting they reported in this paper is some qualitative study. They recruited 5 clinicians, 2 of which are consultants with 11 years experience combined, and 3 of which are registered with 3+ experience each. So these clinicians synthesize some timelines of the patients. So 34 timelines created, following some clinical vignettes. So for evaluation, they first used the foresight model, the KCH one, to process each timeline and then present the next 5 disorder concepts. And the clinicians scored the relevance of each concept to the timeline. So they break the metrics into 5 categories when it's evaluating the first prediction, the first 2 prediction, the first 3 prediction, first 4, and first 5. And they reported a high relevancy from 97 to 88. So here is an example of a patient timeline where 4 of the 5 disorders were considered relevant by the clinicians. So this is a patient with whose sex is male, unknown ethnicity, age is 64, and with memory impairment, with recurrent falls, etc. And weight is the feature importance. This timeline is provided to the foresight, and the foresight predicted that the next 5 concepts are normal pressure, hydrocephalus, etc. And this hypertensive disorder systematic arterial is incorrect, but it's because this concept is common in this patient's age group. Another use case of this pre-trained model is that it could be used to model the full trajectory of the patient. So the model is given just the demographics variables, like the age is 43, sex is female, ethnicity is Black. The model is then able to generate the full trajectory of that patient. So this paper incorporates various structure concepts to model training and can scale to more patients and more concepts, and is helpful for simulating patient timelines. But it's also limited in terms of the long-term forecasting. They only reported the qualitative results, but not some quantitative results. Handling hallucination could be a challenge, and it would need some improvements. And the feature importance were provided as numerical values, and which is not as interpretable as human language. Next, I'll move to the second paper, zero-shot health trajectory prediction using transformer, that published in NPJ Digital Medicine this September.
Discuss that paper a little bit.
Yeah.
What do you think of that paper?
This paper? So the model they use is quite old. It's just GPT-2, and they actually didn't report the context length of the model. The next paper reported is 2048 tokens max length, but this one didn't report that. And its task is quite the metrics it used to evaluate is quite simple. It's just in terms of the quantitative, it's just the next concept prediction, and it was actually not very desirable. I think its highlight is having some clinicians to actually evaluate it, so that, and it designed a very nice metric, which is relevancy. And
their baseline LSTM.
yeah, the LSTM. Yeah.
In the interface, you can choose what the next most likely of different types of concepts is.
It will display them in the order of probability. So this,
That's for disorders, but if you would say the model should predict, yeah, something else, is it just filtering?
yeah, it's just filtering. It's just making the next token, just one token prediction. And well, maybe not just just the concept, the SNOMED concepts. So they include disorders, medication, procedures, and the symptoms and findings.
They also have medication concept.
Yeah.
And you know how salience is computed?
I saw it's very simple. I don't remember it.
Probably their attention or maybe.
I think it's more simple than that.
Ratings.
Not sure. They use it. They had a reference for that, but it's quite old paper, 2010. So I don't assume it to be, yeah.
Where did they publish?
Yeah, yeah. Oh, another.
How useful.
Well, if a doctor is having a patient come in and the doctor just enter this information, and the doctor can see what's the likely disease the patient has.
I don't think the doctor works that way.
To be fair, the doctor's gonna take one look and go, oh, I know this already.
And I saw the archive version of this paper. It was near the end of 2022. So that could be the reason why it's so a little antique.
What's the title of the paper?
It doesn't evaluate it, it's just computed, it's only computed. So when a feature is more important, whether it has a higher value, it means it has a higher contribution to the so the feature importance is computed based on each concept, each of this predicted concept. So the salience, if I click salience, it's gonna show some gradient for this sequence. Yeah, I think it's doable. And we could probably come up with some more sophisticated and useful methods. And like I said, it only use, maybe we can consider using some natural language to do the interpretation as well. Yeah.
Do the authors make any suggestions on how these diagnoses or probable diagnoses could make it to those who are not practitioners? So if you need to make a judgment call to see a practitioner, that could be more efficacious than WebMD.
Yeah. I don't think they reported a lot of practical use of this model. They reported I think that was justified by having some conditions to actually qualitatively evaluate the prediction of the model.
Okay, so
But,
would you
yeah.
describe this paper as more exploratory?
Yes. Well, personally, I wouldn't use I wouldn't use this myself for diagnosis, but I think they advertise it as something that could be used in practice. Yeah. If there's no more questions, I move to the second paper, the zero-shot health trajectory prediction using transformer. So AI has the potential to improve healthcare, but has limited widespread adoption. Some limiting factors include the lack of large label data sets, which is expensive to develop, and the limited system capacity, which is challenging the healthcare delivery. And ETOs represent enhanced transformer for health outcome simulation. It's a novel method designed to enhance AI adoption in healthcare, and the goal of it is to address limitation that hinder the aforementioned aforementioned challenges for large data sets and system capacity. The core concept of this study is the patient health timelines, and similar to the previous paper, it's also a sequential ordering, chronological ordering of the patient's records. But here, the tokens could, by the way, this paper does not use any text data. This paper, though, use the lab values. So the token could be the patient admission, medication, and time intervals and lab values. Here is a overview of the pipeline they use. So this study only used the MIMIC4 dataset. It split that into 90-10 training and test set and tokenized that in and then training a model. So a patient could have many tokens like the inpatient admission, the emergency, the ICD SEPSI code, and here's the ICU admission and transfer to SICU. And SOFA is a test, and this Q3 is the third quantile of that value of that lab values. And then there's a 6 to 12 hour interval, and then another lab with some quantile values, etc. The training, it used 8 GPUs for 36 hours. Yeah, it didn't report what kind of GPU it used, just the number. And then it's able to predict the inpatient mortality, readmission, and some other tasks. So the MIMIC4 dataset was used in this study. It covered 400,000 hospitalizations in more than 200,000 patients. The special thing about their data preprocessing technique is that they didn't use any modification, cleaning, or imputations, because they believe that the large data set and proper tokenization methods could allow EVOs to handle the noisy input just like how we handle how GPT handles the text. It has multiple prediction tasks. So the ICU mortality prediction, the length of stay prediction, the readmission probability prediction. It also estimates the first day sequential organ failure assessment SOFA, or that was a score, SOFA score, because it basically could predict any tokens in the sequence, as well as the diagnostic rating group, which contains 771 categories. They categorized the healthcare foundation models into two. One is the clinical language models, which is a specialized subset of large language model trained on clinical notes, biomedical literature, and they could be used to extract drug names, summarization, and predicting clinical outcomes. The other one, which is what they are doing, is the foundation models for electronic health medical records. It's tailored specifically for EMR data analysis on structured data and focus on tasks such as patient phenotyping outcome prediction. They they believe that the evos can eliminate the need for fine-tuning or label data for accurate inferences or predictions, and they demonstrate the inference across various tasks without any training. The data set, this Mimic4, again, that's from 2008 to 2019. So they use multiple tables and Mimic for the patient's admissions, ICU stays, and lab events. Oh, they to construct the patient health timelines, they just arrange everything in tokens. So each token is a distinct unit of information for that patient. And the tokens are arranged chronologically based on timestamps, which is age. They have a special handling of the timestamp, and they represent the age as a 64-bit floating point, so that they have, because for the ICU, for the ICU timelines, they could be hourly data, etc. So they had to use very precise way of representing them. So they also design a dedicated way to represent each event and ICD code. Instead of representing each concept by one token, they could represent each concept by multiple tokens. And for the lab values, the numerical values, they represent them using quantiles. So for each, they have 10 quantiles. And they also have some time interval tokens representing the interval between events. So here's a tokenization process. So there are 3 layers. The first layer is just a very general. So we have admission event. The patient has admitted to the hospital, and then the blood pressure was tested, and there's a medication administered, and there's a diagnosis. And 72 is the age of the patient. So 23, 27 is the time of this event, and 28 is time of this event, etc. And each event is further broken into more details. So there's the type of admission, and then the emergency, and then the ICD code, and then the blood pressure. The QA is the quantile. So this is probably the upper bound of the high blood pressure, and this is the low blood pressure that's measured. And then ADC, inpatient, discharge, etc. Then for the next layer, they remove all of the age, and then the time is then represented as the time interval, so 30 minutes to 1 hour, and 30 minutes to 1 hour here, 2 hours to 6 hours. And this sequence will be provided to the model to do the next token prediction. So here's some examples of how they represent different codes. They have special design for different kinds of codes. For this ATC code, example, A10B802, A10 is 1 token, and B is 1 token, and then A02 is another token. For IC10, the E11, E11.65, the E11 is 1 token, 0.65 is another token. And similarly for this 0FB03ZX, for this one, every token is every digit is 1 token. Here is a distribution of the top is for the time interval token. The y-axis is the type of token, and the x-axis is the percentage of that token in the whole corpus. We see that most of the time interval tokens are 2 hours to 6 hours. And the bottom is the distribution of the quantile tokens. Again, x-axis is the percentage of that token in the whole corpus. And we see that Q1, the first quantile is appearing for the most of the time. So for ICD-10, they could be represented by various number of tokens, like 1, and the minimum of them is 1. And for medications, at least 1. But blood pressure is 3 because it's blood pressure token and followed by the high and low of the blood pressure. And then ICD-10 PCS, there's at least 3 tokens, lab tests, at least 2. They have the special demographics block, which has 6 tokens, the sex of the patient, the marital status, the race, and some more. And for modeling, they use GPT-2, the same as the previous paper. So for each patient's timeline, they appended an end of timeline token. And when doing training, they follow the popular way of natural language, which is concatenating all timelines into one long sequence and then do truncation afterwards. And they predict the next token. And they also did some hyperparameter search, which I will talk about that in the results section. They have 2048 sequence length maximum. Here are some results for the predicted modeling. They found it competitive with the SOTA models. So it's better than the SOTA for ICU mortality and ICU mortality of sepsis. For ICU mortality, the best AUC is 0.918, and their model is 0.927. For ICU mortality sepsis, the best one is 0.762, and their performance 0.889. So one interesting thing they did, they also compared to GPT-4o, and they found their models performing better than 4o. So I'll talk about how they make the comparison. So they first give GPT-4o a task, instruction of the task, and then the patient timeline. The patient timeline is only represented, it's the same input as the pre-trained model they used. So here's a problem with many definitions for the lab results, for diagnosis, and also about how they tokenize the lab results, how they make the quantile for the lab results. And here's the patient sequence that they provided to GPT, which is I believe is just the tokens they in the raw form they provided to their pre-trained model. And they found their models performed better than GPT-4o. So the EVOs is 0.765 for AUC, and GPT-4o is 0.632 at temperature 0.5 and 0.622 at the temperature of 0.3. In conclusion, this paper using innovative approach to do the modeling for the medical data from EMRs, and the model exhibited the zero-shot ability, and it's able to generate patient sequences. The future studies could be performing some few shot evaluation and better visualization of the layers of the models for future importance, and also including clinical node data, imaging data, etc. And thank you for the presentation. Let me know if you have any questions. Yeah.
I saw the author also compare the proposed method against the transitional machine reinforcement executions.
Yeah.
And they report the comparative performance. And then they also report that the proposed method is better than the before.
Yeah.
But that is the now.
This
Do
one.
you think that I'm just thinking that maybe but in terms of the efficiency, you can just use the conditional machine approach. It is way more efficient. And because they cut down the token space, they just limit the token, right? They only mathematically code those tokens.
Sorry?
They only allow the model to code the token they specify. And reduce the token space.
Oh, reduced, okay.
Yeah,
Oh, yeah,
so
okay.
It means that when you compare it to GPT-4, the
Yeah.
GPT-4 can generate some natural language such as reasoning as an interpretation to the result, to the picture result. But this one, this model can just generate the whole thing, but we cannot make it generate the natural language anywhere.
Yeah. And I also think that it's a little tricky in terms of evaluating the GPT-4o. I think a fair comparison would be to just give some description instead of this coded sequences to GPT-4o.
So they don't use the same input for GPT-4o.
Oh, they do use the same input for GPT-4o, but that's after converting to this very sophisticated format. So it's difficult for GPT-4 to understand. Yeah.
It's a simple thing, but GPT-4o generally isn't being used as the most powerful model anymore. Is there any report on it being compared against Sonnet?
Right, they haven't reported that.
Okay.
Yeah.
For doing kind of patient selections, like selection on those patients that have
I think for this model, they just used all patients.
but what if there are some patient, since we are looking, that these projects are looking at the full trajectory. What if patient, enter the health system, leave some data and then lost follow-up.
Yeah, I think that
Yeah.
that would be a limitation of this theory.
Are those models available?
No. Well, this one should be available. This one, because it's trained on Mimic. They have the. I saw the code is available. I'm not sure if the model.
Availability, I guess, about the model on the.
The code is available, but I'm not sure if the model is available. We could ask.
If they do mimic, should be same as, I'm gonna have to go through mimic approval, release the model.
That's true.
For the previous, the first one, the model is also not available.
That is just trained
They
on.
have the interface.
Yeah. Yeah, that one's definitely not available. This is the second paper. Yeah. It's very not accurate.
Really not interested.
I found it. They found a way to get away with it with the relevancy scoring.
They are not impressed. You have to go into that for me, because that is actually better than, my when I was in the lab, that's better than the results I got. So can you elaborate?
This one?
Yeah. Look at what they got, I mean, 0.3, 0.21.
That's a little hard for me to see. Is that a variance or what?
Uh,
is that?
That's a recall.
That's the score, this score, the precision and recall. The,
And also, they also already relaxed the window to 30 days.
yeah. This 30 could be 30 days, this is 365 days. This is the rest of,
I would ask them to provide a baseline, just when the 30 days window, do a chi-square, most associated concept across all the patients.
Okay, that's
What will be their results, just based on the association, co-occurrence or something like that.
that could be good already.
Right. Just based on co-occurrence, I think, given a 30 days window. And
stats.
they managed to publish it less than digital health. What's the lessons learned for the stuff you are doing?
Having a doctor to evaluate is very useful. And also have multiple institutions.
I think the second paper, at least they predict the modality. That's actually more.
Yeah. And they use numerical values.
Representation really matters, like how you represent the sequence data. Do they really show like this kind of representation actually matters quite a lot,
No,
having those time interval token.
they don't have the ablation study.
Thank you.